The 12-kilometer mark beneath the Earth's crust represents the maximum limit ever reached by human engineering on the Kola Peninsula, the point where the planet's natural resistance began preventing any further progress. Although it may seem that surpassing this threshold would depend solely on financial investment, time, or technological advancement, physical reality imposes far more complex barriers. As the descent continues, the environment becomes hostile at extreme levels. Temperatures exceed 400 degrees Fahrenheit, causing metals to deform, drilling equipment to fail, and solid rock itself to behave almost like plastic under the colossal pressure. The anomalies, however, became even more pronounced in the deeper layers. During the ultra-deep drilling operations, researchers encountered water-saturated fractures, unexplained gas emissions, and rock formations that challenged the prevailing geological theories of the time. The objective now is to understand the maximum depth humanity can excavate and uncover the mysteries hidden within a void where human presence has never been possible. This raises a common question. Why have we never been capable of drilling through the planet from one pole to the other, while logic suggests that powerful machines and persistence should be enough? Reality reveals that at 7.5 miles deep, the Earth establishes its own boundaries. At that depth, conventional scientific understanding gives way to a scenario where high-strength steel becomes malleable. On the Kola Peninsula, decades of work were invested in carving a path toward the center of the Earth, but every additional foot drilled pushed the practical results further away from the original mathematical models. Up to roughly 4.25 miles, the operation remained relatively stable, but upon reaching nearly 40,000 feet, the environment's behavior changed drastically. Temperatures climbed to 356 degrees Fahrenheit, nearly twice the amount scientists had projected for that layer, making the heat unbearable for measuring instruments. Visualize the magnitude of this operation. A gigantic platform supported a column of steel pipes weighing hundreds of tons, with a drill bit reinforced by industrial diamonds at its tip. Under normal circumstances, such equipment could cut through granite with ease, but at extreme depths, geology itself transforms. Beneath pressures exceeding 1,000 atmospheres, the walls of the shaft were crushed inward, and the granite began to take on the consistency of thick, viscous honey. Just a few movements were enough for friction to raise the metal's temperature to critical levels, resulting in the immediate loss of its structural integrity. The greatest logistical challenge involved maintenance. To replace a single worn-out component, the entire length of the pipe column had to be hoisted back to the surface, an exhausting process that consumed 24 continuous hours of labor from the crew. But during the time the drill bit remained absent, the planet literally managed to close its own wound. The viscous rock, subjected to immense pressure, simply flowed back into the opening. The shaft narrowed again, forcing engineers to re-drill sections they had already crossed the previous day. It became an endless battle against the Earth's interior. The engines roared under immense strain, while the metal pipes twisted like thin wire. Sometimes, the steel simply could not endure the pressure and snapped deep inside the shaft. The drilling project at Kola revealed that the Earth's crust is far more dynamic and complex than theoretical models had predicted. The greatest surprise was the presence of water at depths where scientists expected to find only dry, dense basalt. Instead, they encountered superheated mineral solutions trapped under extreme pressure, proving that liquid could penetrate and remain inside deep fractures even beneath miles of incandescent rock. The most revolutionary discovery, however, was biological in nature. Fossils belonging to 24 species of ancient plankton were found more than 20,000 feet below the surface. These microorganisms, preserved inside rocks dating back 2 billion years, challenged the assumption that such delicate structures would be destroyed by heat and pressure. The evidence suggested that life on Earth not only emerged much earlier than previously believed, but may also have occupied deep ecological niches, forcing a complete re-evaluation of the limits of the biosphere and the resilience of primitive life forms. But to reach this truth, human beings had to overcome almost unimaginable technical challenges. Flammable gases began emerging from the shaft alongside the water. Helium, hydrogen, and methane literally burst upward from the depths, creating a constant threat of fire. Every new foot drilled became not only a scientific achievement, but also a true test of endurance. Workers wearing protective helmets constantly monitored the sensors, because any accidental spark inside such a gas-saturated environment could trigger an instant catastrophe. Scientists realized they had uncovered a gigantic natural deposit whose existence no one had even suspected. The planet's interior revealed itself as a living and dynamic system. However, while some researchers celebrated the biological discoveries and the deposits of rare gases, others began noticing strange anomalies. The deeper the drill advanced, the more the nature of the sounds coming from the depths changed. Sensors installed to monitor the movements of the Earth's crust began recording something that seemed to defy rational explanation. These recordings soon became the foundation of one of the most terrifying legends in the history of science, causing millions of people around the world to shudder. A wave of mystical fear spread across the planet when Western newspapers began publishing stories about horrifying recordings supposedly coming from the depths of the Earth. According to the reports, at a depth of 7.5 miles, researchers had lowered an ultra-sensitive microphone into the shaft and heard disturbing sounds. The recording spread across the world almost instantly, gaining increasingly terrifying details with each retelling. But what did the instruments truly capture at the deepest point ever reached on Earth? The truth turned out to be far more complex and intriguing than any urban legend. At the Kola superdeep borehole, acoustic sensors were indeed used. Engineers needed to monitor the operation of the drill and record even the slightest tectonic movements. At such extreme depths, sound propagates in a completely different manner than it does on the surface. Dense rock, compressed under monstrous pressure, behaves like a gigantic resonating chamber. Every movement of the granite plates or the dry snap of metal breaking apart was transformed into terrifying noises. Inside the surface laboratory, the atmosphere was one of constant tension. From the speakers emerged a deep, continuous hum, suddenly interrupted by sharp screeches and piercing metallic groans. Under the extreme heat of the Earth's interior, sound waves became distorted, almost beyond recognition. In addition, the pumps responsible for circulating the drilling fluid generated rhythmic pulsations that, when blended with the noise of the turbines, created a sound mass resembling the distant moaning of a crowd. It is important to note that the audio recordings which later fueled urban legends were fabricated montages, but the genuine recordings captured by Soviet scientists were equally unsettling, revealing the acoustics of a planet fully alive and in motion. At the 12-kilometer mark, the rock exists in a state of perpetual flow. The sound resembles a massive ice field slowly cracking apart, amplified thousands of times over. David Guberman, the director leading the project, later recalled these episodes with a degree of irony, though he admitted that some phenomena were difficult to explain. On one particular occasion, the drill suddenly plunged into an unexpected void, contradicting every geological map indicating solid rock in that section. The event caused an abrupt pressure fluctuation and a unique acoustic impact. Far removed from any mystical explanation, researchers had encountered an unprecedented geological phenomenon, a zone where gases trapped under colossal pressure shattered the surrounding rock, generating a deafening roar. Every acoustic anomaly pushed the engineering team into a state of maximum alert. Often, complete silence coming from the sensors was even more terrifying than violent noises, because it indicated either a total communication failure or a catastrophic breakdown of the drilling equipment. Although the experiment conducted on solid ground proved that drilling through the granite shield toward the Earth's core was virtually impossible, scientific ambition did not fade. Faced with the immense thickness and extreme heat of the continental crust, a new strategy emerged. Logic suggested that drilling should occur where the Earth's crust was thinnest. Attention then shifted toward the ocean basins, in the hope that the seafloor would provide easier access to the mantle. However, researchers had not yet anticipated that the ocean depths concealed dangers capable of turning the entire project into a technological nightmare. The reason for attempting the operation in a marine environment, despite the enormous logistical complexity, lies in one astonishing numerical difference. While continental crust can reach depths of 25 miles, beneath the ocean floor it narrows to only 3 to 4 miles, theoretically the perfect shortcut to the planet's interior. In practice, however, this short journey transformed into a true technological nightmare. Specialists found themselves confronting physical pressures capable of destroying any machinery almost instantly. One of the major milestones of this exploration was Project Mohall, launched during the 1960s, carrying an extraordinarily ambitious proposal to drill directly into the floor of the Pacific Ocean from a floating vessel. The complexity was immense because the drill first had to travel through more than 11,000 feet of water before even touching the seabed and beginning to break through the rocky layers beneath. The operation resembled an attempt to drill through a concrete structure from the top of an enormous building, where any ocean movement or gust of wind could compromise the stability of the entire system. One of the most critical moments of the expedition nearly resulted in the project being shut down prematurely. During the experimental procedures, the vessel was struck by a massive underwater current that had previously been unknown to scientists. This invisible force in the depths generated such intense tension on the anchoring cables that they reached the very limit of their resistance. The technical crew watched in apprehension as the drilling tower structure tilted dangerously. If the metal column had collapsed, the impact of hundreds of tons of steel against the hull could have caused the vessel to sink and brought the entire project to an end. Disaster was avoided only because of the captain's expertise and the precise performance of the positioning engines. However, the obstacles were not limited to the waters themselves. The moment the drill reached the ocean floor, it became clear that marine geology was merciless. Instead of finding soft sediment layers, the operators collided with basalt formations whose hardness rivaled that of diamond, causing the cutting tools to wear out completely after only a few hours of use. In addition, every drill bit replacement became an absurdly complex operation. The crew had to hit the exact same tiny opening on the ocean floor while operating several miles above it. Japanese scientists aboard the vessel Chikyu pushed the technology even further, creating a floating platform equivalent in height to a 30-story building. They used computerized systems to keep the ship positioned in exactly the same spot, with an accuracy measured in mere inches. Yet even this technology could not fully overcome the force of nature. Researchers discovered that in regions where tectonic plates meet beneath the ocean, gas pressure became so intense that the wells began expelling incandescent mud, jamming every mechanism. In the end, humanity came to realize a bitter truth. The thin oceanic crust is even more difficult to penetrate than the thick granite shield beneath the continents. We have never managed to drill completely through this surface, but while some attempted to open narrow shafts, others created gigantic craters capable of inspiring fear solely because of their dimensions. These artificial abysses became so deep that they began generating their own climate phenomena and even threatening the machines operating inside them. But what truly happens inside a hole larger than an entire city? Imagine a gigantic crater so deep that a 5-story building at its bottom appears no larger than a matchbox. This is the case of the famous Mir mine in Yakutia, whose depth exceeds 1,600 feet. This man-made abyss is so colossal that aircraft are officially prohibited from flying above the area. And this is not merely a precautionary measure. There is a legend claiming that the hole transformed into a trap capable of literally pulling aircraft from the sky. When a helicopter flies over the massive crater, physics itself enters a dangerous game. The enormous volume of cold air trapped inside the mine creates powerful downward currents. The aircraft loses lift and begins falling into the abyss as though being pulled into a void. The air no longer supports the rotor blades, and the helicopter is dragged into the funnel like a tiny splinter caught inside a whirlpool. In reality, the danger posed by turbulence is very real. Pilots can completely lose control. It is a genuine physical phenomenon that has turned deep mines into some of the most dangerous places on Earth. But it is not only the air that behaves strangely. The size of the machines operating at the bottom is astonishing. Giant trucks larger than a 3-story building slowly move along spiral roads carved into the walls of the mine. Seen from above, they resemble tiny insects. If one of those machines loses its brakes, stopping it becomes impossible. There was once an incident in which a gigantic truck lost control on a slippery section of the road. Only the driver's instantaneous reaction, steering the multi-ton colossus directly into a rock wall, prevented it from plunging into the abyss. Curiously, deep mines begin creating their own microclimates. While the surface may be suffering from suffocating heat, the bottom can experience intense cold, with fog becoming so dense that drivers can barely see the hood of their own vehicles. At the American Bingham Canyon mine, whose depth reaches nearly 4,000 feet, engineers faced an even more terrifying phenomenon: gigantic landslides. In 2013, approximately 65 million tons of rock collapsed there. The event was so powerful that seismic sensors registered an impact comparable to a small earthquake. Human beings created these holes in search of diamonds and copper, excavating the earth for decades. But no matter how much soil we remove, we are still merely scratching the surface. Even the deepest mines on the planet remain insignificant marks compared to the immense thickness of the Earth's crust. But why, despite all our technology and gigantic machines, did we stop? Why did humanity stop digging deeper and begin searching for other alternatives? The answer lies hidden within an invisible limit that we ourselves created, along with new projects that today seem insane even to the boldest engineers. We now stand before the final frontier, where the question is no longer about money, but whether the planet itself can withstand our curiosity. Have you ever wondered what exists exactly beneath your feet, 25 miles below the surface? That is where the Earth's mantle begins, a gigantic ocean of incandescent rock occupying 80% of our planet's volume. We have sent spacecraft to Mars and deep into outer space, yet throughout all of human history, we have never managed to pierce through the thin surface of our own planet. Today, the competition to explore the Earth's depths has entered a hidden and sophisticated phase in which specialists employ cutting-edge technology in an attempt to overcome previously impossible barriers. The depth records no longer belong to the Kola Peninsula. Modern records were established by oil drilling operations in Qatar and on Russia's Sakhalin Island. The Odysia well, for example, surpassed 40,000 feet in total length, but with one peculiar characteristic. These drillings are not strictly vertical. Such structures resemble highly complex labyrinths that begin with a straight descent before executing smooth lateral deviations extending for miles beneath the ocean floor. It is an exercise in surgical precision. The operation can be compared to attempting to manipulate a flexible needle from an enormous distance in order to hit a narrow hydrocarbon target hidden beneath layers of rock. During one of these ultra-deep extension projects, a singular event challenged the logic of the technical crew. At a certain point, the drill stopped responding to commands, and telemetry data indicated that the end of the equipment was rotating in the opposite direction of the drive system, as though internal planetary forces were twisting the machinery itself. The later diagnosis revealed that the monumental length of the pipe column had created an enormous torsional effect, transforming the steel into a colossal spring loaded with energy. Upon encountering greater resistance, this accumulated force was suddenly released, placing the integrity of the entire structure at risk. The incident served as a practical demonstration that, at such vast scales, the behavior of metals becomes unstable and difficult to predict. This naturally raises the question of why drilling is not kept strictly vertical at similar depths. The answer lies in a deadlock involving both technical and financial limitations. At a depth of approximately 9 miles, the sheer mass of the steel pipe column would become so immense that the material would collapse under its own weight. Humanity has therefore reached the physical resistance limit of the materials currently available. To surpass this frontier, entirely new composite alloys and cooling systems capable of enduring temperatures approaching 570 degrees Fahrenheit would be required. Even so, science is already advancing Project M2M, whose goal is to establish humanity's first direct contact with the Earth's mantle using autonomous robots designed for hostile environments. This is considered one of the most dangerous experiments ever planned because the consequences of breaching the layer that isolates the planet's internal heat and pressure remain uncertain, generating debate among researchers about the possibility of triggering significant geological disturbances in the intervention area. Thank you for watching our channel. If you enjoyed this content, leave a like and share it with others. See you next time.